Now for a story that might hit some of you a little too close to home. If you've ever dropped your cell phone into a puddle and had it fry, and taken it into Sprint or AT&T or whoever, and told them, hey, I don't know what happened, but my phone just stopped working. They say, well, did it get wet? No, it didn't get wet. I didn't do that. And then they take off the back cover and they take out the battery and they look at this little sticker in there and they just look at you like, this phone's been wet. It's not covered under warranty. And then you get to pull out your credit card and buy a new cell phone. Good times, right? Now, what let them know that? The answer is sitting in front of you, waters of hydration. Now, some compounds, especially our ionic ones, they have, a certain shape and a certain amount of charge to them. Well, remember, the outermost portion is all going to be electrons, and it's going to have a negative charge to it. The water molecules, sometimes with certain molecules, can come along and they stick to it in a very specific pattern with a continuous and repeatable number of waters. Now, this is different than my arm when it goes into the water. When my arm goes in water, random number of water molecules. But these crystal lattices end up having specific numbers of waters that coordinate with your metal. And they are called waters of hydration. If they can be a random number, they aren't waters of hydration. But when we're talking about water molecules that stick on in a reproducible fashion, water of hydration. Now, you can push them off with heat a lot of the time, and that's what was going on with that. Your phone, when it was manufactured, they had heated up a metal salt that has waters of hydration normally until it pushed off all the water molecules. That made the energy levels be some specific gap. Then the water molecules, when they stuck to that metal, they pushed those energies around a little bit, and if you change the size of the spacing between your lower level and your upper level, it changes how much energy is needed to get between them, and that changes the color of light that it absorbs. It's a color change. And so waters of hydration are going to lead to color changes a lot of the time. You've probably seen this before with some of your food beverages and other sorts of dyes, but that's often a different effect. Okay, now let's go forward and see what's going on here. So those waters of hydration, in order to write them, we'll write our ionic substance first, in this case BaCl2, and if it has waters of hydration, you put one of these center dots, and then you put the number of the waters followed by H2O. Make sure that 2 is a subscript. If you start doing nonsense like writing H2O or H20 or any of the other nonsense, you'll be hearing from me, just like editors of newspapers frequently do. Don't do that silliness. Make sure you're writing it because these notations mean something. Okay, so barium chloride exists on its own, but if it has the waters of hydration, we have to specify that. Now, how do we know when that's going to happen? We don't. We tell you when waters of hydration will be there. We'll see some examples of waters of hydration in the lab course this year as well, but it's not something you would necessarily predict, not at the Chem 1 level for sure. Now, here's how you'll write that as a word. You're going to write the name, so barium chloride, and then you're going to put a number prefix before the word hydrate. So barium chloride, 6 waters, so hexahydrate. And of course, more memorization for us to do. Luckily, these are not terrible to memorize. They go pretty obviously. Hemi is the weirdest of them. Half, because no, you can't attach a water molecule or half a water molecule to a molecule. You can't do that. But you could have 2 of these metals sharing 1 water, which means that it's like there's half per 1, right? It's like they're splitting a pizza. There's 1 pizza, but it's split between 2 people. That's what we're talking about for the water of hydration there. Mono is 1, di is 2, tri is 3. If you've ever played the game Tetris, this will be easy for you to remember because how many squares are in each of the pieces in Tetris? That's actually where the name came from. 4 squares are in each of the pieces in Tetris. Penta, 5, hexa, 6, hepta, 7. This is one that you probably haven't had a lot of experience with just because we don't use the number for 7 very often. And octa, you certainly have learned about hexagons, pentagons, and octagons. So you should be able to remember octagon and octa as well.